Hey, my name is Alexander Galvez-Vega. I'll be presenting my part of my team's slides on large language models. Now I'm going to split it into three parts. The first part being why did we focus on this? In a natural language processing class, that might seem unusual, but it's really not. Natural language processing, in many ways, is a bit of it can be a bit of a subsector sometimes in terms of artificial intelligence, in that it focuses on a really specific aspect of computer science, which revolves around enabling computers to understand, interpret, and generate and manipulate language, everyday language, whether that be it through text or speech. And large language models represent a culmination of these efforts in many ways by bringing multiple core natural language processing tasks together and bringing upon them a major shift from like the early days, whatever, where most computer science was really more rule based and structured, and now resembling its compute resembling a little bit something closer to understanding the relationships of words in a provided corpus. So something to note, though, whatever, getting into a really brief history, is there's many influences in this respect, whatever, that have led to this moment. Linguistics is incredibly important for one. Ferdinand de Saussure, the one of the fathers of modern linguistics, really explored the meaning of relationships between language elements and the nature of language through this idea of it being a system of science. And that really gave later computer science leverage to break things down into rule-based formats, whatever, that could be used by machines in this pursuit of being able to communicate properly between man and machine. And Noam Chomsky took this even further in the 1950s by setting up and defining the rules found in sentence construction, allowing for this rule paradigm to occur at all. At the same time, however, our obsession with automation was happening around this period, and a little bit before World War II, Alan Turing invented the Turing machine, which allowed for the first bricks of the computational standards of computer science to exist at all, and then later used a machine to combat another machine, the Enigma machine, in World War II, allowing the Allies to win the encryption battle process during that time. And it really showed, it conveyed how we can use these automatons to complete tasks that would traditionally be associated with humans. And as this is going on, just exploring this even further, there were many innovations that allowed for this pursuit of artificial intelligence to occur at all. And one of them is how hardware has been able to get smaller and smaller. One group of inventors, John Bardeen, Walter Bertrand, and William Shockley, invented the transistor, which really shrunk down and allowed for electrical signals that we associate with like the binary 1 or 0, that became the basis of a lot of our computer systems that ever came in very pivotal here and allowed us to shrink down um, machines in a way that would really allow more researchers to explore machine learning algorithms and everything else. And another important person to note, although we'll hop back to him a little bit later, is Ted Hoff, who invented the microprocessor that allowed things to shrink a little bit further in the 80s, I believe. Yeah, no 70s, 1970s. So getting into it, though, rewinding just like a tiny bit, in the 1960s, our first experimentations with chatbots occurred, and that early precursor to what we have now is ELIZA. ELIZA was not very good, but it did represent this early experimentation with rule-based systems that allowed for humans to interact with machines. It had this clever way of mimicking and mirroring back questions back at the user. Now, it wasn't really true artificial intelligence or anything, but it became a focal point in this pursuit of it. And in this 70s and 80s, we were able to take these notions and incorporate probability theory in creating machine learning algorithms, and stuff like not what we're familiar in class started appearing, like naive Bayes classifiers. And our modern examples, we've talked about this extensively in class. Whatever you take data for training as the inputs, and then after the algorithm processes it, you get an output, whatever that in the modern examples in class, whatever could be like a spam or not spam for mail, right? But then other things started appearing that we've also discussed in class, like term frequency, inverse document frequency, and vector space models, which allowed this ability to represent documents numerically and embedding and embed and tokenize in a way that would allow machine learning algorithms to move away from rule-based systems and try to have these machines learn in a way whatever with a deeper context understanding, which is why you got a lot of the semantic network stuff at first, and then a little bit later in the early 2000s there was because we're trying to mimic humans, whatever, humans decided to focus on humans in the sense that we started talking about neural networks, and a person that was pivotal to this was Jeffrey Hinton, who created this concept of the backpropagation algorithm that allowed for these neural networks to work. And they took inspiration from the human mind, where the whole idea was these neural networks were supposed to resemble neurons in a sort of way. And then a lot of innovations continued occurring because that he later was able to create the convolutional neural network, which took things a step further, and then on AlexNet, which was a deep revolution in the world of neural networks, because a lot of these things, while they were sequential in nature, it improved upon the ability to maintain memory of previous inputs and contextualize word meanings from large corpora. But the problem with this is that in terms of long-term information, long-term context, there was still a bit of a gap. And the paper in 2017 called "Attention is All You Need" really dealt with this. It took this concept of moving away from sequential operations and used a transformer architecture to take advantage of parallelization, and this allowed for long-term context to be held. And I'm gonna move into a very brief overview of LLMs in this respect, because that's what allows them to occur and work so well. So essentially, an LLM is going to have a encoder and decoder, and inside these and subsectors of both sides, there is a attention feature which allows words to have context for all the other words and the operations and their order in a certain way. And what you'd expect from before still exists. You still tokenize and embed those words, whatever, but the attention now remains, whatever, and then it gets fed into a feed forward aspect that refines everything that's going on. And so after inputting and outputting through this transformer architecture, it gets very impressive what we could see. So now I'm gonna pass it on to my teammate. Thank you for taking the time to watch this presentation on my side. Thank you.
Hello, my name is Ken Ferreira, and today I will be discussing what large language models, or LLMs, can do in the field of natural language processing. Natural language processing, or NLP, focuses on how computers understand and work with human language. LLMs are one of the most important advancements in this area because they allow machines to interact with the language in a much more natural and intelligent way. So what exactly are large language models? LLMs are AI systems trained on massive data sets such as books, websites, and articles. These datasets contain a wide variety of language, which allows the model to learn patterns in how humans communicate. This includes grammar, sentence structure, and even context, like how the meaning of a word can change depending on the situation. Because of this, large language models are able to understand and generate human like text. For example, they can write essays, summarize information, answer questions, and even engage in conversations like human beings. However, it is important to note that they don't truly understand language the way we do. Instead, they rely on patterns and possibilities learned from data to reduce the responses. As mentioned earlier, large language models are trained on large data sets and learn patterns in our language. Now, let's look at how they work in action. First, a user inputs a prompt, which is typically like a piece of text. The model then analyzes the context of the input, looking at how the words relate to each other. Next, it predicts the most likely next word. For example, if a user inputs the sky is, then the model will most likely predict blue, because that is a common pattern that data has seen. After that, the model continues predicting one word at a time. This process is called token by token generation. It keeps repeating this process, building a sentence step by step until it forms a complete response. This all happens extremely fast, which is why it feels like the model is thinking or responding in time. But in reality, it's making a series of very advanced predictions based on probability. There are many ways that large language models can be used as tools. For example, they can generate text such as essays, emails, or even computer code. This is especially useful for students or professionals who need help writing or organizing ideas. They can also pull important information when answering questions, which makes them useful for research and data analysis. Large language models are commonly used in chatbots, allowing users to have full conversations that feel natural and human-like. Other capabilities include translating text between languages, summarizing long documents into shorter versions, and performing sentiment analysis, which is relevant to the field of natural language processing, which determines whether a piece of text is a positive or negative. Some popular tools that use large language models include ChatGPT, Microsoft Copilot, Google Gemini, Claude, etc. Large language models are used in many real-world situations across different industries. For example, they're used in chatbots for customer support, which they can answer questions and help troubleshoot issues quickly. They're also used in data analysis, where they process large amounts of text data and extract useful insights for research or decision-making purposes. They're also used in data analysis in businesses. Large language models can assist in analytics and automate reports and even help predict trends such as sales. In healthcare, they can analyze patient notes and assist with documentation, helping professionals save time. And in education, they use AI tutors or tools that can help students better understand concepts and the material and also complete assignments. These are just a few examples that show how impactful and versatile large language models are in real world applications.
Okay, so I'm Emmanuel, and I'll be going over the live demonstration of how LLMs can be used for NLP. And so in our demonstration, we're gonna show how the LLMs, ChatGPT and Gemini, can be used for basic NLP tasks such as translation and summarization, and also more advanced tasks that we did in for the class assignments, including sentiment analysis and text classification. So yeah, we'll begin with showcasing the general NLP capabilities of LLMs, which are going to be summarization, so summarizing a long article to a short summary, and translation, which will be translating English into Spanish specifically. So as we have here on the right side, we're loaded up on ChatGPT, and I've pasted the text, and so I just told it just read it, don't give me anything yet. So it read and digested decent sized text. And then I told it summarize in 2 to 3 sentences. And we see here that it gave us a 3 sentence summary. AI is changing the industries and some concerns about it. And it was a good summary for this decent sized text. And then for the translation, we did it on Gemini. So posted the text here and then told it just to read it, or Gemini just LLMs, if you don't give them specific instructions, they do just give you like summaries, and so it can be kind of annoying to use them, but as long as you control them, it's all right. So we told it translate the text into Spanish, and we got the Spanish translation showing. So that showcases how LLMs can be used for very basic NLP tasks. And then for advanced NLP tasks, we'll show sentiment analysis. So how it can analyze the sentiment of a text, whether it's positive or negative. And then also text classification. So classifying a text if it's either sports, text, or tech or politics related. So we came here and we had pasted this chat, pasted this text. It was, I bought this laptop, and then it crashes constantly. The battery drains. So, frustrated sentiment here. And I just told it just to read it. And then we asked, what is the sentiment? And the sentiment is negative. And it gives us the explanation. It's negative because it expresses frustration, mentions crashes, and regret about the purchase. So we say here sentiment analysis of ChatGPT of a small text. And then here we go to Gemini. And so now we're looking into text classification. So the latest advancements in artificial intelligence and machine learning. So we see here it's a tech related one. I told it just to read for now. And it still gave us a little 1 sentence summary, which we didn't want, but it's okay. And then classify the text into one category. And we see here Gemini classifies it as a technological in the technological category. We had Gemini do just one more to verify that it can do this at a constant rate, because we don't care if it's just going to give us one time accurate response. We want it to consistently give it, or there's no point. So the team secured a dramatic victory in the final minutes. Just told it just to read it, classify the text, and we see it's sports because it's a victory and thrilling. The fans are excited. So that's how it can be. LLMs can be used for basic and advanced tasks. So, and then we get into why LLMs are powerful. We saw there one model. So ChatGPT was able to do, multiple tasks. Gemini was able to do multiple tasks. No training was required. Just putting the text, asking for it to do the task. It's faster and more flexible than just traditional NLPs, and it can work across domains. And then we see And then for the last slide, we can see a little comparison of traditional LLPs to LLMs, where traditional NLPs need multiple models, like such as TF, IDF, and naive bias, while LLMs just need their one model. Traditional NLPs require pre-processing and training, while LLMs just require you to put the text and then ask for it to do the task. And then traditional NLP need separate models to do separate tasks, while LLM, a ChatGPT, can just handle. ChatGPT could have done all four tasks if we asked it to, but we at least separated to see how ChatGPT could do and Gemini could just do. And that's a little demo of how LLMs can